equals 27. So the equation of my tangent line is negative 12x plus 27. And 27 makes sense for my problem since I know it's going to cross way up there. Oops, sorry. 27. You should have been able to do that without seeing that. Okay, let's go. So we found the equation of the tangent line. Now we want to identify delta x, dx, dy, delta, okay, here. So delta x and dx, if you look back at our definitions, delta x equals dx, and I just told you in words it's the change in x on both functions. I should have gave you the little formula. It's just b minus a. It's your new value minus your original value. Should have put that in here, b minus a. So part B is identifying all of this stuff. Delta x is the same as dx. It's the b minus the a, so it's 1.9 minus 2, which is a negative 0.1. Okay, two of those are done. dy. Nope, let's go, it doesn't matter. Delta y next. Delta y, you look at your formula, it's the change in y values on the original function. So it's the f of b minus the f of a. So if I apply it to this problem, I want f of 1.9 minus f of 2. F is my original function. So all I've got to do is go back to my 11 minus x cubed, plug in 1.9, and we already know that when we put the 2 in, we get a 3. So I've just got to plug the 1.9 in, or I can even trace to 1.9 and have it tell me it's 4.141, since I already had it in there. 4.141 minus 3, 1.141. Okay, now the dy. The dy was that special one. There were two ways to get it. We are going to do both ways. They should come out the same. So the dy is the change in y values on the tangent line. The tangent line y values. So just real quick, it's y of b minus y of a. So it's y of 1.9 minus y of 2 using the tangent line equation right here. Something's still there. So plugging 1.9 into the y equation. So doing that, well, we know the y of 2 is a 3 still. So negative 12 times the 1.9 plus 27. I got 4.2 minus 3 is 1.2. Okay, the big connection here is that we could have found that dy value without knowing the tangent line if we use this other definition. It's f prime of x dx. And x is our original a value, because the b is the x plus delta x, and this says f prime of x. So the other definition would be f prime of x, which is our a, times dx. Well, f prime of 2 and dx, well, f prime of 2 just requires me to go back to the derivative equation. The derivative equation we found, remember I told you to write all of them down, negative 3x squared. So I'll plug 2 into that, negative 3 times 2 squared, and the dx, we found that our very first part here. Dx is a negative 0.1. And hopefully negative 3 times 2 squared, just like times a negative 0.1, 1.2. I think the whole point of this section was to show this little shortcut here, so that we could avoid all of this work here. Okay, and then the last thing we need is the error at 1.9. Glad I started a new page, or I'm still running out of room. And the error is how far apart these two functions are at that second y value. This distance in here is our error. So that is f of b minus y of b. So the f of b value, well, we already did it over here, 4.141 minus the y of b, we did it down here, 4.2. That's the putting in the 1.9 into the original and into the tangent line. So our error came out 4.141 minus 4.2, negative 0.059. Must be indicating that the original function is lower than the tangent line with the negative there. Okay. The rest of the section, which is most of the homework problems, are actually very, very easy. This isn't bad if you look back at those 4 definitions and just keep track of your 3 equations you have going on, the original, the derivative, and the tangent line. They won't be too bad. Okay, the rest of this section, kind of review with a little small twist. So example 2, we are going to find an equation for the differential dy. And we're going to use that second definition, dy. The definition we're going to use is that dy equals f prime of x times dx. So with an equation, we are going to have x's in our problem. We're not going to actually get numerical answers like we just got done doing. So if I gave you the equation f of x equals 1/3 x to the 5th, and I want dy, all I have to do is do the derivative of f. Derivative here, little power rule, 5 comes down, 5/3 x to the 1 less power times by dx. So all I'm doing to get a differential is doing derivative and sticking a dx on the end. The only difference is I'm not calling this y prime, I'm calling it just the differential dy. Do not call this y prime because it's not quite y prime because the dx is over here. To be y prime, the dx would have to be underneath. So it's just a little notation, housekeeping there. If I had y equals, which y is another way for f of x, doesn't matter, 4 sine 2x plus 3x to the negative 1/2, and I want the differential dy, I've just got to do the derivative of this and times by a dx at the end. Okay, so 4 is a multiplier. Derivative of sine is cosine times by the derivative of the angle plus the next derivative. The 1/2 comes down as a multiplier, so that'll be a negative 3/2. X subtract 1, I'm going to get negative 3/2. That, because there's 2 terms here, I definitely want to have parentheses with the dx. Simplifying, this will be 8 cosine 2x. This will be minus 3/2 x to the negative 3/2. All that times dx. So if you want an equation for a differential, just call it dy, do the derivative, attach a dx on the end, you're done. Okay, the last example you are going to find an equation for the antiderivative y. Okay, starting with the differential. So if dy, the differential of y, equals 15x squared dx, we want to be able to find the antiderivative. Well, what I need to start with is the derivative. This is almost the derivative. All I've got to do to make it the derivative is get dx underneath here. And I can do that by dividing both sides by dx. So dy over dx equals 15x squared. That's like saying y prime equals 15x squared. Now I want to do antiderivative. What function gives me that derivative? So y equals, leave a space, start with the exponent. You know it starts one higher than this. Now I got to ask myself, 3 times the number I put down here has to give me a 15. So I know I have to have a 5 down here. And then a plus c for any constant that might be here, because when I take the derivative, it goes to 0. So going from a differential to an antiderivative, all we do is divide by dx to kick it over here, and now we have the derivative function. Very, very easy. Try one more. dy equals 5x squared minus 2x plus 1 dx. Again, antiderivative, I need to know what the derivative is. Well, I know it's just this right here. Am I going to force you to divide by the dx every time? No, you don't have to. You can just jump right into doing each term separately. But for note purposes, I will kick it back to derivative form. So dy over dx equals 5x squared minus 2x plus 1. Now I'm ready for antiderivative. So I know this term has a cubed. So now I need to know 3 times what number here has to give me a 5. Well, 3 times some number has to give me a 5. Divide by 3, I can see it's 5/3. Minus, this one has to have an x squared. And if I check the derivative, the 2 would come down. 2x to the first, that's exactly what I have, so I don't need anything there. And this, what's going to give me a derivative of 1 is x, and then I need a plus c. Okay, that's all I've got. Your assignment is going to be page 187, number 1, 7 through 23 odd, and 25 to 39 all.